Welcome to Energy Stored by a Capacitor. We are already familiar with the concept of work in electric circuits. We know that work is the charge multiplied by the voltage. And if we have a look at the units, we can see that work is measured in joules, charge is measured in coulombs, and voltage is joules per coulomb. When a capacitor is being charged, we are connecting it to a power supply. Here is a simple cell. We can regard the negative terminal as being a source of electrons and the positive terminal as being a deficit of electrons. When the capacitor is connected, the electrons flow through the wires because they are attracted to the positive terminal, and they start to collect on the plate. The electrons that are in the opposite plate are attracted to that positive terminal as well. So they flow through the wire and arrive at the positive terminal, leaving behind a deficit of electrons. These charges spread out across the plates. And that's because these plates are electrical conductors. And inside an electrical conductor, electrons are free to move around. So for example, if we have a spherical object and we build up a localized area of charge, this material, being a conductor, allows those charges to repel each other and move apart until they are evenly distributed across the surface of the material. Now that these plates already have a small buildup of charge, it is slightly harder for the electrons to flow and for new electrons to arrive at those plates because of the repulsive effect of the electrons that are already there. And this is true for the buildup of charge on the positive plate as well. So if we draw a graph and observe the charge build up, this will increase. It will increase quickly at first, and then more and more slowly as it becomes increasingly difficult for more charges to be added. And it takes more energy to add more charges, the more charge buildup there is on the plates due to this repulsive effect. Eventually, when the capacitor is fully charged, the voltage across the capacitor will be equal to the voltage of the power supply. So if we draw a graph of charge, we can do it against voltage, and it will produce a line like this. We can see here from this equation that the area beneath the graph would be the energy or the work done. The shape of this graph is a directly proportional linear relationship between voltage and charge. This is because when there's only a small amount of charge on the capacitor, it takes only a little energy for that to be added. But when there is a higher charge, that will have taken a much higher energy for that charge to accumulate. The area beneath this curve is the work done, and because it's a triangular shape, it's half the base multiplied by the height, half the base, which is charge, multiplied by the height, which is voltage. We also know that capacitance is defined as Q over V, or charge divided by voltage, and we can substitute this into the energy equation. So here's the basic energy equation. We can substitute in a value for Q and get half CV multiplied by V, or V squared, or we can substitute in a value for V, Q over C, or Q squared over C. You may sometimes see W written as E in some textbooks, but otherwise these are the standard equations.